Light waves all travel at the same speed, and there it is. And this is how we think that light is acting like a particle. Photon is a tiny little package of energy, a particle of light. You're going to need to know to determine where electrons are located in atoms. So this sounds like we're talking about physics, but it's really important we get a little background in light before we talk about electrons. And so, in fact, this is where we get the theory. The current theory of electron configuration is from the study of light waves. So every element will exhibit a unique spectrum, and it's like a little fingerprint of different wavelengths of light that indicate where electrons are located in orbitals. So let's first talk about light. When I say light, I want you to think not, hey, turn on the light switch, electromagnetic radiation. And that's what this spectrum represents. And so there are several different forms of electromagnetic radiation. You've heard of radio waves, you've heard of gamma rays. Those are the two extremes of this spectrum. And then right in the middle is visible light, which is what you're most familiar with. That would be from red to violet. You're familiar with that spectrum. And then in between, we've got microwaves and we've got infrared. That's, you might have heard of heat waves. And then next to visible, we've got ultraviolet and then X-rays. So all of these are light. And they all travel at the same speed. They just have different wavelengths. And obviously, as we move from left to right, we get to shorter wavelengths and they become a bit more dangerous. So let's talk about the basics of a wave. I'm going to draw a wave here for you with a fairly long wavelength and then a very short wavelength. You're familiar with the terminology of wavelength. And our symbol now for wavelength is this lambda. I'll write that down. That is a Greek letter L, and it's like I do a slide with a kickstand. That's how I make a lambda. So wavelength is represented by lambda for L. And then frequency, this looks like a V. It's really a Greek letter N for nu. So that refers to how fast waves are coming at you. And so that would be the number of waves per second. So the unit for frequency is hertz, and the abbreviation is Hz. And a hertz is a per second. So how many per second are moving by a fixed point? Now, all waves have a wavelength and a frequency. Now, light waves all travel at the same speed, and there it is, 3 × 10⁸ meters per second. So that's how fast all of these waves are traveling. So they all travel at the same speed. What makes them different? Wavelength and frequency. And we see these are inversely related. And here's our equation that we're going to use to calculate wavelength or frequency. So let's do an example of a blue light wave. So I've got a wavelength of 485 nanometers. Now, nano is one of our metric prefixes we don't use a whole lot, but that is 10⁻⁹. So really, really short wavelength, and we are wanting to find the frequency. So we've got our equation. Now let's rearrange to solve for frequency. You want to divide both sides by lambda, right, to get the frequency by itself. So frequency is the speed of light divided by wavelength. So plug in your values. The speed of light is 3 × 10⁸ meters per second. And then the wavelength, I can't plug in the nanometers. I need to plug in meters so that it will cancel out in my equation. So watch this little trick. 485 nano means 10⁻⁹ meters. So I converted really from nanometers to meters. Now what happens with my units? Meters on the top, meters on the bottom will cancel. And my units cancel, meters on the top, meters on the bottom, and so my frequency is 6.19 × 10⁻⁴ hertz. And you say, well, that's a really big number. Well, there are a lot of waves. Like if you have blue light hitting you right now, that's how many waves per second are hitting you. Let's do one other concept. We've got light. One of the things that we notice is it has properties of waves, frequency, wavelength, but it also has properties of particles. So for example, if you hit metal with light at certain frequencies, electrons will begin to fly off. And this is how we think that light is acting like a particle, because it's dislodging electrons. So light is like a wave and a particle. And let's consider light as little packages, little quantities, little quanta of energy, and call that little particle a photon. So if you hear me use the word photon, I'm referring to light as a little tiny particle. Now we can actually calculate the energy of one of these little particles of light, and this is the Planck's equation. So E, energy, is in joules. That's our energy unit, J for joules. And then H is the Planck's constant, which will be given to you. And then this is our frequency. Nu is frequency, and that would be in hertz. So let's calculate the energy of our little blue light wave. Now our frequency was 6.19 10 to the 14th hertz. So I'll go ahead and use that. So we're going to write our equation, and then we'll plug in our values. So H is 6.625 10 to the minus 34th joule seconds. And then the frequency, 6.19 10 to the 14th. Now a hertz is nothing more than a per second. Okay, so I will say seconds to the minus 1, if that makes sense. When we multiply seconds on the bottom, seconds on the top, we'll be left with joules. So energy in joules is 4.10 10 to the minus 19th joules. That is energy. And you say, well, that's a tiny number. Well, a photon is a tiny little package of energy, a particle of light. And so I hope that helps you understand waves, frequency, wavelength, speed, and energy. Stick with me. We're going to get to electrons really soon.